Okay, so this is the next problem. A uni-processor computer system has only two processors. Okay, so there are only two processors, both of which alternate 10 millisecond CPU burst with 90 millisecond IO bursts. Okay, so what's happening is that for both of these processes, for 10 minutes, 10 milliseconds, the process will run on CPU, and for next 90 milliseconds. Okay, so for 10 milliseconds the process runs in CPU, and for the next 90 milliseconds the process does IO, input output. Okay, both the processes were created at nearly the same time, so both the processes are start at the same time. The IO of both processes can proceed in parallel. Okay, so for both of these processes the input output can go in parallel. Okay, for CPU it cannot be parallel because there is only one CPU, but IO can run in parallel. And which of the following scheduling strategies will result in least CPU utilization over a long period of time? So you have to tell that which of these processes will give least CPU utilization, and we have this first come first serve, shortest remaining time, static priority scheduling. Okay, all these things. So what we will do, we'll look one by one for both of these or for all of these and see what happens. Okay, so I'll just make this timeline first so that it's easier to see what's going on after that. Okay, so suppose this is 0, and we know that all these processes start at 0. Okay, and let's talk about first come first serve first. Okay, so we are talking about first come first serve, that is option A first. And what happens is, suppose we'll name these processes P0 and P2 P1. Okay, so these are the two processes. So what will happen in first come first serve? So suppose P0 comes first, so for first 10 milliseconds, okay, P0 will run out here, okay, in the CPU, and then it will start its IO. Okay, so then it will, what will happen, the CPU will uh, get P1. Okay, for another 10 PU will be running. Okay, but what you should know that just after that this thing ended, P's IO for P0 has started. Okay, so IO for P0 has already started out here, and after P1 is done we have IO for P1 starting after that, and then these IOs can go in parallel. Okay, and then this IO goes on for 90 milliseconds. Okay, that means that if you started your IO out here, it will go on up till 100 like this. Okay, this is the 100 milliseconds. So this IO for P0 will go on up till here. Okay, and then what about the IO of P1? So IO of P1 will go on up till what point? Let's say this point. Okay, 110, because this will also need 90 90 milliseconds from here. Okay, and this is 20. Okay, I should write here 20 because this is 10, so this should be 20. So that's it. Okay, and then when the IO of this P0 will be finished, okay, what it can do is it can get back to CPU, and then P1 will start once the IO of P1 is stayed. So this thing will go on. Okay, and what you have to see that for what time the CPU is idle. So CPU is idle out here. Okay, so this is the time when CPU is idle, not doing anything. So what is CPU utilization in this case? So in this case the percentage of CPU utilization is how much? So if you look at up till here, after this the same thing repeats. Okay, P0 P1 and this thing, so the cycle will repeat from here. So for this first 100 seconds you see that for first 20 seconds, the first 20 milliseconds the CPU is being utilized. So it gives you the idea that it's 20 by 100. Okay, into 100 if you do, so it gives you 20%. So CPU utilization in this case is 20%, that is first come first serve. So I'm going to write it out here, 20% utilization in first come first serve. And then let's talk about shortest remaining time first. Okay, so in this case what happens is the one with the shortest remaining time gets priority, gets higher priority. Okay, so let's have this P0 and P1, and since the CPU burst is same for both of them, it is 10 milliseconds, and suppose P0 runs like this out here. Okay, and as it will run, its remaining time will decrease, but for P1 it's still 10, so obviously P0 will get this complete uh, 10 milliseconds. Okay, and after that it will start IO and P1 will get 10 milliseconds. Okay, because it's shortest remaining time. Okay, and then the same thing. So what happens is that in this particular example, in this particular case, shortest remaining time behaves just like first come first serve. Okay, just think about it. Okay, P0 comes, and um, okay, if in the beginning both of them need the same time, so we give priority to someone, let's say P0 or P1, we can give it to anyone, and it ran for 10 milliseconds, and then P1 ran, and then there was this waiting period, and then again the same thing. So it doesn't behave different from, it doesn't behave differently from first come first serve. So that means this one also gets 20%. What about static priority scheduling with different priorities of the two processes? So it's again the same thing. Okay, if in this particular case you will see that this static priority scheduling behaves the same way. It's not different in this case also. Why? Suppose one of them gets static priority. Static priority means the priority doesn't change, it remains the same. So if P0 got better priority, it will run for 10, and then P1 for 10, then this waiting period, and then the same thing. And it turns out that this one will also need just 20%. Okay, there's 20% CPU utilization in this C case also. And then what is important is that this round robin scheduling. Okay, so by, since you are given choices, by elimination you can guess that this must be round robin, and we'll see how that thing is true, because we are going to see what happens in round robin. So suppose I draw this this thing again. Okay, this is my timeline. So I've drawn my timeline again, and then what we are going to do is we're going to start round robin. Okay, so this is round robin. Okay, so this is round robin, and time quantum is 5 millisecond. Okay, so the chunk you give, the time chunks you give are 5 millisecond, 5 milliseconds. Okay, so what will happen at 0? Suppose you give 5 millisecond to P0. Okay, so 5, and then comes P1. Okay, so P0 cannot start its IO right now, can it? No, because it will start its IO only after it has finished these 10 milliseconds of CPU bursts. Okay, so after that P1 runs for 5 milliseconds, so this is 10, and then P0 runs. Okay, so this is up till 15. Okay, now P0 can start its IO because it has finished its 10 milliseconds. So 5 out here and 5 out here, 10. So now what we can have is this thing, we can have IO for P0. Okay, and this can go on for how long? Next 90 milliseconds from here. Okay, and then after this P1 gets, and up till 20 P1 will run, and then again P1 gets P1 can start its IO now from here on. Okay, so now P1 can start its IO, and this will go on for another 90 milliseconds. So when will the IO of P0 finish? From 90 milliseconds from here, that means at 105. Okay, and at 110 the IO for P1 will finish, because 90 from 20 will be 110. So, and then what happens is, once the IO of P0 is over out here, then P0 can again get the CPU. Okay, and then the same thing starts again from here. Okay, so the cycle is up till here, and from here onwards the same thing is repeated. Okay, so now what you see, if you want to write down the percentage CPU utilization out here, so CPU is used for these first 20 milliseconds, that is true, but out of how much? 105. Okay, in the case, in these earlier cases, we had 100 in the denominator because it was from this 100, but now it's from this 105, and if you will find this percentage, it is definitely going to be less than 20%. So which means that the least CPU utilization is in the case of round robin scheduling in this particular case.